Well, you see, before we begin wandering through these vast cosmic frontiers, let me ask you something simple, but strangely unsettling. Have you ever looked up at the night sky and felt, even for a moment, that the universe might be far larger, far older, far stranger than anything the human mind was built to grasp? Because that's where our little journey starts, right at the edge of what we can understand, and just a breath away from what we can only imagine. Um, Perhaps tonight you're here because a quiet question has been lingering somewhere in you. What lies beyond the light we can see? What secrets were whispered into existence long before humans learned to listen? And that's the thing, every ancient photon drifting through the cosmic microwave background, every subatomic particle smaller than our language allows us to describe, they're all clues, gentle reminders that the universe doesn't just give us answers, it gives us humility. It invites us to wonder, to explore, to dream slowly, softly, like we're tracing the edges of a map that's still being drawn. Our path tonight, well, it's part science and part quiet reflection. Each chapter of this cosmic journey will take us to places where knowledge thins out, where the known dissolves into the unknown. The horizon of the observable universe, the hidden dimensions curled up beneath reality, the ghosts of eras before time began. These are the thresholds we'll walk together. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And while you're settling in, tell me, where are you listening from tonight? What part of the world is sharing this moment beneath the same sky? It's always fascinating to see who's joining us from all around the world. So let's continue. Well, let's drift into chapter 1 together, slowly, as though we're stepping out onto a shoreline where the light itself becomes thin. You see, when we talk about the horizon of the universe, we're not speaking of a line we could ever walk toward. It's not just a boundary out there, but also a kind of mirror of our own limits. And as strange as it sounds, this horizon is shaped not by walls or edges, but by time, by light, by the simple fact that the universe has only been shining for a finite number of years since its beginning. So when we gaze outward, we are not really looking into space. We are looking backward into time. The farther we look, the further back the clock unwinds. We grow older, clocks tick, and the universe grows older with us. But the light from those first galaxies, well, it has taken billions of years to reach our eyes. And that means there is a limit to what can have reached us at all. There are regions, vast regions, where the light has not had enough time to cross the ever-stretching fabric of space. Whether it is a region of familiar galaxies or a place flooded with exotic structures, well, whether it exists at all in the way we imagine, we simply cannot know. The universe expands, and here's the curious thing, it expands faster than the speed of light in the distant reaches. Not the galaxies themselves breaking the cosmic speed limit, but space itself stretching between us. So even if a distant star were to scream its light toward us with all the urgency of creation, that light would never close the gap. The distance grows faster than the light can cross it. And that creates a horizon, a kind of cosmic event line beyond which no signal will ever arrive. And this horizon is not fixed. It shifts as the universe evolves. It grows, it changes, it reveals, and it hides. What we call the observable universe is just a bubble, a fragile bubble of visibility inside a vast ocean we will never touch. Some of the galaxies we can see today, faint as whispers, are already slipping away, carried off by the expansion, moving beyond our reach forever. The universe is not just expanding, it is carrying information away like footprints washed by a rising tide. Um, you might imagine standing on the shore at night, looking out across a dark sea, trying to see the distant lantern of a ship, and the ocean is swelling, and the ship is drifting farther even as you stare. That is the way the universe behaves. We observe only what light can deliver, and light is a slow messenger in a world that keeps stretching. And, um, well, this raises a question, a quiet one, a philosophical one. If there are galaxies beyond our horizon galaxies we will never see, never detect, never hear from, do they belong to our universe at all? Are they part of our story? It's not just a scientific puzzle, it's a mirror held up to our longing for completeness. Humans want to know everything, to gather, all the pieces, yet the cosmos places a soft hand on our shoulder and whispers that some things are simply hidden, not by mystery, but by the laws of space-time itself. When we talk about the universe we can observe versus the universe that exists, those two are not the same. The observable universe is a sphere defined by light, travel time since the first glow of creation. The total universe, well, it may be infinite or finite, curved or flat, looping back on itself like the inside of a vast, unending hall. It may contain realms with clusters of galaxies beyond counting, entire regions where the arrangement of matter follows patterns we have never imagined. But we will never access them, not just because we lack the technology, but because the laws of nature themselves forbid it. And here lies a point that always makes me pause. The fact that we see only a tiny fraction of what exists does not make the rest unreal. It's like being inside a fog. You can see only a few meters. But the world beyond continues to exist, full and vivid. The horizon of the universe is a cosmic fog, a boundary of light. What lies beyond may be familiar or utterly foreign, but it does not depend on our seeing it to be true. And that leads us deeper into the strange dance between light and expansion. The speed of light is constant, but the fabric of space is not. It pulls and stretches, so the horizon is not static. Over millions of years, we will see new regions of the early universe brought into view, not because new galaxies appear, but because the ancient light that has been traveling toward us finally reaches our eyes. We are always receiving delayed messages, postcards from a distant past. That ancient light is not a visitor from space, but from time. Yet even as older light arrives, some regions recede entirely, moving beyond what cosmologists call the commoving horizon. It means that in the far future, say, trillions of years from now, Milky Way and a handful of nearby galaxies may be all that remains visible to whatever beings might still exist. The grand cosmic web will fade from view as expansion carries almost everything away. The universe will grow quiet. The night sky will empty. And the ancestors of those future beings, our descendants, perhaps might never know how vast the universe once appeared. We live in a privileged moment when the cosmos still whispers its structure to us, when the afterglow of the Big Bang, the soft radiation spread across the sky, still lingers like an echo of the universe's childhood. This afterglow, this cosmic microwave background, is our deepest window. It is not just a picture, it's a fossil. The moment when the universe first became transparent, when light was allowed to travel freely, is still visible to us as a faint, cold glow. And if we could see beyond that, if we could peer past that ancient veil, we might know what existed even earlier. But that boundary, sometimes called the surface of last scattering, is another horizon, another limit, another cosmic reminder that knowledge ends where opacity begins. And, the concept of a horizon invites an even more subtle realization. Horizons in physics are not static things, they are dynamic, shaped by the expansion of space and the energy within it. Just as black holes possess event horizons that trap all light, the universe itself possesses cosmological horizons that trap regions of reality from ever touching one another. The expansion driven by what we call dark energy accelerates the separation, stretching space-time so quickly that communication becomes impossible across vast cosmic gulfs. So in a sense, we live inside a very large but very finite bubble. Not a bubble with walls, but a bubble of time. A bubble defined by what can reach us, not by what exists. And that is a humbling thought. It's not just about astronomy or physics. It is about perspective. It's not about what's out there. It's about what we can know. It's not about the edge of space. It's the edge of understanding. And as the universe continues its expansion, parts of it disappear from our causal reach forever. That word causal matters because it reminds us that science is not just about seeing, it's about interacting, about exchanging signals, about causality, connecting one point to another. But beyond the horizon, causality breaks. Those galaxies and structures and perhaps entire cosmic domains may as well belong to another reality entirely. And this, strangely enough, brings comfort as well as wonder. There is something profoundly human about standing on a boundary we cannot cross and letting imagination travel instead. Science gives us explanations, but the horizon gives us something else. It gives us humility. It gives us the awareness that the universe is not just larger than we think, but larger than we can think. The horizon also shapes everything we predict about the ultimate fate of the universe. Because what we cannot see, those far regions beyond our reach, might hold clues, or mass, or energy fields that influence the expansion. The universe we observe is only a fragment of a grander structure. Whether the whole thing is flat or curved, finite or infinite, smooth or chaotic, well, we craft our best models, and then we watch as new light arrives to refine them. And if you listen closely, there's a gentle question hiding here. If the universe is so vast that we cannot see most of it, are we truly at the center of anything? Or are we simply at the center of our own horizon, a horizon that moves with us, shaped by our moment in cosmic time? Not just a physical center, but a perceptual one. And that's the thing. This first step, this first chapter, isn't really about horizons as boundaries. It's about horizons as invitations. They invite us to imagine what lies beyond, and they invite us to accept the beauty of not knowing everything. The universe expands, light travels, space stretches, and we remain here small, curious, awake beneath a vast and ancient sky. As we drift onward, perhaps we should consider a deeper question. If the universe has horizons shaped by its laws, then what about regions where the laws themselves might differ? Could there be realms where physics changes its dialect, where the rules we rely on are only local customs? And that thought leads us naturally, quietly into the mysteries waiting in the next chapter. Well, as we ease ourselves from the fading edge of the cosmic horizon, something else begins to shimmer into view. Something quieter, but in its own way, far stranger. That thought we left hanging in the air, that possibility that the laws of physics themselves might not be universal, well, it leads us into a landscape that is not just vast, but varied, not just expansive, but profoundly diverse. And here, in this second great chapter of our wandering, we're stepping into a realm where the rules we trust, the constants we measure, the patterns we think are woven into the fabric of reality might be nothing more than dialects of a much larger cosmic language. You see, when physicists talk about the multiverse, not the version from films, but the version whispered about in the fine mathematics of string theory, they imagine something like a terrain, a vast, undulating terrain filled with valleys and peaks. And well, each valley corresponds to a different set of physical laws. That is the landscape. Not a metaphorical one, but a literal mathematical map of possible universes. In some valleys, the forces behave just as they do here. In others, the constants shift ever so slightly. And a small shift is enough to turn a universe into a silent, starless ocean. It's not just mind-bending, it's heart-bending. Because it reminds us that our universe, the one we inhabit with all of its structure and stability, is just one arrangement among countless possibilities. So imagine for a moment that you are drifting across this landscape. You float above different regions, and in each region, the rules that govern reality rewrite themselves. Not just the strength of gravity or the mass of the electron, but the very ability of atoms to form, the very ability of stars to shine. And you might wonder, quietly, why our universe permits such delicacy. Why do atoms hold together? Why do stars burn in long, steady pulses? Why does chemistry unfold in ways that allow life to emerge? If the constants changed only slightly, just slightly, then the universe might collapse into itself or expand so violently that matter never gathers. That delicate balance is not just an accident. At least some physicists argue it may not be an accident. It may be a selection effect, a kind of cosmic filter. Out of a vast landscape of possibilities, only a tiny number of regions allow something as complex as us to exist and wonder. And here's the thing. The landscape theory doesn't begin with speculation. It begins with the internal logic of string theory. That logic suggests that space-time has extra dimensions curled up in tiny, invisible shapes. And the shape of those hidden dimensions determines the constants we observe. So in one region of the larger multiverse, the dimensions curl up into one shape, giving one set of laws. In another region, they curl differently, producing an entirely different reality. It's not just one universe, but many. Not just one set of rules, but an enormous library of them. And, when we think about this, there's a strange humility that settles over the mind. The laws of physics that feel so solid beneath our feet might be nothing more than local customs. Not absolute, but regional. Not universal, but provincial. Whether it exists beyond our horizon or not, this idea unsettles our sense of certainty. We grow older, clocks tick, and yet the universe may keep its deepest truth out of reach. For instance, in some possible regions of this landscape, electromagnetism might be stronger or weaker. If stronger, atoms might collapse. If weaker, atoms might never hold. In some regions, nuclear forces might refuse to bind protons together. A universe without nuclei is a universe without chemistry, and thus without stars, planets, oceans, and, without stories. The landscape predicts not just variation, but radical variation, the kind that changes everything from the birth of galaxies to the possibility of life. And in some valleys of the landscape, the vacuum energy might be enormous, so enormous that space would expand exponentially in the blink of an eye. Matter would be torn apart before it could ever form. In other valleys, the vacuum energy might be deeply negative, collapsing the universe before time even gets the chance to unfold. So when you think about it, we live in a remarkably special corner of possibility. That isn't to say we are special, but that our conditions are. It's not just improbable, It's profoundly improbable. Um, and yet, the landscape invites us to rethink what improbable even means. If the total multiverse is vast enough, perhaps infinite, then even rare regions like ours are inevitable. They appear not because the universe desires life, but because probability across a large enough canvas allows everything that can happen to happen somewhere. It's not just one attempt at physics, it's a tapestry of attempts. But here is where things become even stranger. The laws we consider fundamental may not be fundamental at all, only stable. They are like the result of a frozen accident in the early universe, a settling of parameters when the cosmos cooled. It's not that we understand the laws, it's that we understand a version of them. It's not that physics is one thing, it is many things, and we are familiar with only a single thread. And this leads us to a question that once asked is impossible to forget. If our laws are not universal, then what is universal? What lies beneath the laws, the constants, the fields? What is the deeper principle that gives birth to this landscape? There must be something beneath, some deeper symmetry or mechanism that allows variation to emerge. That is where the mystery truly lives. Take, for example, universes where stars cannot form because the fusion processes would never ignite. A cosmos without stars is a cosmos without heavy elements. And without heavy elements, there are no planets. Without planets, no oceans. Without oceans, no life to sit beneath a sky and wonder where the boundaries of knowledge fade. In these valleys, the universe is dark, not just in appearance, but in possibility. It is a silent universe. And then there are universes where stars form too quickly, burning hot and short. There might be fireworks of brilliance, but no long, calm stretches of stability where evolution could take root. A universe full of short-lived stars might shine brightly, but briefly a world where time is too shallow for complexity to unfold. So when we look at our own universe, we begin to sense a kind of quiet luck. Not luck in the mystical sense, but statistical luck. If the multiverse is real, then it is not surprising that conscious beings find themselves in one of the rare regions that supports consciousness. It's a bit like asking why life exists on Earth and not on the Sunday. Earth has the right conditions, the Sun does not. And in the multiverse, our universe might simply be the Earth of cosmic possibilities. And that raises an even more subtle question. If the multiverse is full of regions where the laws differ, can we ever detect these other regions? Can we ever confirm they exist? Or is this a theory we must contemplate without touch, a truth we can only infer from the narrowness of our own existence? Well, physicists have suggested that gravitational waves, or the faintest patterns in the cosmic microwave background, might contain the scars of collisions between universes, ancient bruises where one bubble of space-time brushed against another. Whether such collisions occur is uncertain. Whether we could detect them is even more uncertain. But the possibility fuels imagination. It makes the multiverse not just a theoretical dream, but a scientific hypothesis waiting for evidence. And if we found such evidence, it would force us to rethink what it means for something to be real. It's not just that our universe might be one of many, it's that reality might be layered, textured, and deeply varied. The multiverse would not just be a place, but a process, an eternal unfolding of different physical arrangements. And in that wider view, our universe becomes one chapter in a much larger story. Not the beginning, not the end, but a single moment where the laws allow stars and time and questions to exist. It's a comforting thought, in a way. It's not just that we are small, it's that we are part of something immensely creative. And if the laws differ beyond our cosmic horizon, then the horizon becomes not just a boundary of observation, but a boundary of law itself. The edge of our view might also be the edge of our physics. Beyond it, the universe might play different music entirely. So, so as we let this sink in, as we drift across this landscape of possibility, another question begins to form quietly, almost shyly. If the laws can change from region to region, then what about the beginning? What about the first moment? The moment before time expanded, before the constant settled, before the landscape formed its valleys? Um, and that leads us gently, almost inevitably, toward another frontier, a deeper veil, a veil not of distance, but of time. The question of what happened before the universe began to expand, before time itself emerged. A mystery waiting for us just beyond the next bend. Well, when we follow that lingering question from the previous chapter, what came before the settling of the laws, before the landscape formed its valleys, we find ourselves standing before a boundary stranger and more elusive than any horizon in space. It is not a line drawn across the cosmos, but a veil woven into time itself. And as we draw closer, we begin to sense that this veil is not simply hiding something. It may be telling us that the very idea of before is softer, more fragile than we ever imagined. You see, when we speak of the Big Bang, we often imagine an explosion, a beginning, a kind of cosmic spark that set everything in motion. But that picture is too simple, too familiar. The more we learn, the more we suspect that the Big Bang is not the beginning in the traditional sense, but a boundary in our understanding. It's not just a point of origin, it's the edge of the map where our equations stop behaving, where space and time lose their usual meaning, where the story folds into something deeper. And if you imagine time as a river flowing steadily from past to future, the Big Bang is not the spring where the river begins, but the mist beyond the spring, the place where the idea of a river becomes uncertain. So the moment we try to peer behind that mist, our concepts falter. We grow older, clocks tick, but near that boundary, clocks themselves lose definition. Time becomes tangled with energy and curvature, and the familiar rules of physics stop guiding us the way they do out here. And, well, this is where scientific proposals begin to diverge, each offering a different glimpse into what might have come before, or whether before even makes sense. Some physicists imagine a universe that bounced. The cosmos contracts over unimaginable ages, shrinking until it can shrink no further, then rebounds in a great expanding surge. In that view, the Big Bang is not a beginning, but a turning point, a pivot, a moment in a long cosmic rhythm of contraction and rebirth. It's not just that the universe expands, it also breathes in and out across cycles that could span trillions upon trillions of years. This bouncing idea carries a certain poetic symmetry. What collapses will rise, what diminishes will return, what fades into stillness will pulse again. But the details are difficult. At the smallest scales, near that pivot point, our understanding of gravity fractures, quantum rules clash with geometric ones. So researchers attempt to merge the two, to build theories where space and time themselves become quantized, tiny grains, rather than smooth continua. In some models, these grains resist collapse, creating a repulsive force that prevents the universe from compressing into a singularity. The bounce emerges from this quantum pushback, and yet even here we face uncertainties. Whether the universe truly bounced, or whether this is simply one possible interpretation, remains a mystery. but it carries an enticing thought. If the universe bounced, then something existed before our universe. Another cosmos filled with its own structures, its own eras, its own stories, lost to us forever. And then there is another idea, one even stranger, the notion that time itself might be emergent, not fundamental, not woven into the bedrock of reality, but arising from deeper relationships, perhaps from the entanglement of quantum information at a level that is more primary than space or time. In this view, asking what happened before the Big Bang is like asking what lies north of the North Pole. It's not just unknown, the question itself dissolves. It's not that nothing happened before, it's that before did not exist as a meaningful concept. It might sound abstract, but consider this. Temperature is not fundamental. It emerges from the motion of particles. In the same way, time might emerge from the ebb and flow of something beneath it. Some theorists argue that the universe's deepest description is not geometric but informational. The web of fundamental events creates the illusion of time's flow, much as still frames create the illusion of motion in a film. And if this is true, the Big Bang was not the birth of time, but the moment when time became a useful, stable property of the universe. Before that, reality may have been a formless sea of quantum interactions with no direction, no before and after. So when we speak of what happened before, we may be applying human language to a realm where that language no longer fits. And then, well, there is yet another idea that before the Big Bang, there was simply no time at all. Not an earlier moment, not a prior state, but an absence. The universe begins not at a point, but at a boundary beyond which the concept of time evaporates. It's not just that nothing happened before, it's that nothing could happen, because the very stage on which events occur, time was not yet present. This concept, in its own way, is profoundly humbling. It suggests that asking for a cause of the Big Bang is like asking for a cause of the number one. It is the first entity in a sequence. Nothing precedes it, because the sequence itself starts there. But still, the human mind resists this. We crave continuity. We search for origins behind origins. We look for the parent of every child, the seed of every tree, the spark of every flame. So when confronted with a boundary like the Big Bang, we instinctively imagine something behind it, something deeper, some precursor. And that instinct has driven scientists to explore whether subtle signals from the very early universe, signals older than light, older than atoms, might still be imprinted in the cosmos today. The trouble is that as we rewind the universe backward in time, the temperature rises, the density increases, and eventually the conditions grow so extreme that even light cannot move freely. The universe becomes opaque. Beyond a certain point, our view is blocked by a kind of thermal fog. This is the so-called limit of the cosmic microwave background, the surface of last scattering, a wall of radiation beyond which photons cannot carry information. So to peek behind this wall, scientists turn to other messengers, gravitational waves perhaps, or patterns etched subtly into the distribution of galaxies. Tiny hints that might betray a pre-Big Bang epoch. Some claim that faint circular imprints in the cosmic background could be scars from events in a previous universe. Others argue that primordial gravitational waves would carry the signature of a bounce, or the mark of a universe that existed before ours. But evidence remains elusive. Whether it exists at all is a matter of intense debate. And yet the search continues, because the question of our beginning is not just scientific, it's existential, it's philosophical. It asks not just where we came from, but what the universe is capable of being. And, and in the midst of all this speculation, one truth emerges quietly. The closer we approach that first moment, the more we press into the Planck epoch, the unimaginably tiny sliver of time where space and time become fluid, the less our current understanding can guide us. It's like trying to describe the inside of a storm using the calm of the sky. Our mathematical tools tremble, our theories clash, the path becomes uncertain. Yet uncertainty is not failure. Uncertainty is a doorway. And through that doorway, new ideas enter. Perhaps the universe began as a quantum fluctuation. Perhaps it tunneled into existence. Perhaps our entire cosmos emerged from a higher dimensional structure, like a bubble forming on the surface of a deeper reality. Or perhaps, in some grander sense, the universe always existed, but not in a way our linear understanding of time can grasp. It's not just that we are trying to understand the early universe, it's that we are trying to understand what it means for something to begin. And as we stand here at the threshold where time becomes uncertain, another frontier appears just beyond. A frontier not of time, but of shape. Because after asking what happened before the first moment, we naturally begin to wonder about the structure of the universe that followed. What is the shape of space? Is it flat or curved? Finite or infinite? A vast plane? A cosmic saddle? Or a looped, boundless sphere? And that question, waiting like a quiet companion at the edge of this mystery, will lead us gently into the next chapter. Well, when we arrive at this question of shape of the true form of space itself, it feels as though we're stepping from the uncertain mists of the beginning of time onto a vast, silent plain. And yet even here, where the universe appears calm and comprehensible, something strange lingers beneath the surface. We're not just asking what space looks like, we're asking what it is. We're asking whether the cosmos spreads out infinitely like a boundless canvas, or whether it curls, loops, folds, and closes back upon itself in ways our intuition can barely follow. So let's walk gently into this mystery. You see, space looks flat, at least that's what our observations suggest. Light travels in straight lines. Triangles in the cosmos behave the way Euclid would have wanted them to. Parallel lines don't meet, not just at one scale, but across billions of light years. And, that might suggest the universe is flat in the simplest sense. But here's the thing, appearances deceive. The universe can be flat and infinite, or flat and finite. It can be curved positively, like the surface of a sphere, or curved negatively, like a saddle, or so slightly curved that the curvature hides beneath the precision of our instruments. The question of shape is not trivial. It determines not just the geometry of space, but the fate of the cosmos. Imagine, just for a moment, that space is positively curved. It would mean the universe is finite, but without boundaries, like walking around the Earth not because it ends, but because it loops. In a universe like that, if you travelled far enough in a straight line, you might return to your starting point without ever turning around. It's not just a poetic idea, it's a possible scientific reality. And if the universe were negatively curved, a saddle shape, then space would stretch outward in ways that amplify expansion. Light beams would diverge. Structures would appear more spread out. Such a universe would be infinite, open, forever expanding without hope of slowing. But our measurements from the glow of the cosmic microwave background show something remarkable. Space is almost perfectly flat, so flat that if it is curved, its curvature must be vast and gentle, stretching over scales far beyond the observable universe. It's like standing on Earth and declaring it flat because the curvature is too subtle to see. That leaves us with a profound ambiguity. The cosmos might be infinite, or it might be finite, but so enormous that its curvature lies far beyond our observational reach. And here is the wonderful, humbling truth. We cannot yet say. We grow older, clocks tick, galaxies drift. But the question of shape remains one of the universe's most elegant riddles. Well, the key to all of this lies in the earliest light, the cosmic microwave background. This light, reaching us from every direction, is like a cosmic blueprint. It carries within it the imprint of the universe when it was just a few 100,000 years old. And the way the tiny fluctuations in that light appear tells us something about geometry. If the universe were strongly curved, the patterns would be distorted, stretched, or squeezed like reflections in a funhouse mirror. But instead, they look balanced, aligned, proportionate. So does that settle it? Is the universe flat? Not quite. Because, this is where the puzzle deepens. Even a finite universe can mimic flatness if it's large enough. If the total cosmos extends far beyond the observable region, then we might be seeing only a local patch, just a few square kilometers, metaphorically speaking, on the surface of a planet too vast to notice its roundness. It's not just that space might be curved, it's that the curvature might lie beyond our ability to measure, and this leads to one of the most elegant concepts in cosmology, a universe that is finite but has no edges, a universe where you can move forever without encountering a boundary, yet the total volume is limited. It might be shaped like a three-dimensional sphere, or something even stranger, a torus, a donut shape, where traveling in one direction eventually brings you back from another. Imagine that. You look deep into the sky, and in the faint glow of distant galaxies, you might, if the universe loops just right, catch a glimpse of your own galaxy, billions of years younger, a cosmic hall of mirrors, not through reflection, but through the shape of space. Whether it exists at all is uncertain, but it remains one of the most enchanting possibilities. And, this geometric question isn't merely abstract. Shape determines destiny. The universe's curvature influences its long-term evolution. A closed universe might one day stop expanding and collapse into a final, fiery end, a big crunch. An open universe might expand forever, thinning into cold emptiness. A perfectly flat universe sits at the razor's edge between the two, a delicate balance that, to many physicists, feels almost suspiciously fine-tuned. So why is the universe so flat? Why is the curvature so small, so close to zero, that it lies within the margin of error of our most advanced instruments? Inflation, the idea that the universe expanded exponentially in its infancy, offers an answer. Inflation stretches curvature toward flatness, the way blowing up a balloon makes any small patch seem level. The larger the balloon, the flatter the patch appears. But even inflation carries mysteries of its own. It explains the flatness we see, but leaves open what lies beyond the observable bubble. The larger universe, outside our visible sphere, could have entirely different curvature, structure, or topology. We see only a tiny island in an archipelago of space. And this leaves us in a beautifully uncertain place. The shape of the universe remains tied to what happened in its infancy. But the cosmos may be too vast, too varied, too complex for us to ever see its entirety. Let me try to paint this gently. If the universe is infinite, then its shape might simply be a flat expanse stretching without end. But if it is finite, then it could be a smooth, closed hypersphere. Or it could be twisted, like a multi-connected space, where traveling straight leads you into yourself. It could even have a complex topology that defies intuition, folding dimensions in ways that break our simple analogies. It's not just a question of geometry, it's a question of identity. What kind of universe do we live in? What kind of cosmic home shelters our stars? Um, and somewhere in this reflection, a deeper question arises, a whisper at the edge of our thoughts. If space can look flat but be curved, then what about dimensions we cannot see? What about directions that are hidden, curled up tightly, waiting beneath reality like unseen threads in a cosmic fabric? We, we find ourselves wondering if the shape of the universe in 3 dimensions is subtle and deceptive. What happens if there are more dimensions than 3? What if space is not merely curved? What if it is layered, folded, compactified? And that thought invites us onward gently into the next frontier, into the possibility that the universe we see is only a slice of something larger. A world where hidden dimensions shape the forces we feel, where space is not just vast but deep. So let's follow that curiosity and let's step softly toward the idea that space may have more dimensions than our eyes can ever reveal. Well, when we step from the question of the universe's shape into the question of its hidden depth, it feels as though we're peeling back a veil thin at first, almost weightless, and discovering that space itself may have a thickness of our senses were never designed to notice. And as we move gently forward from that last thought, the idea that our familiar 3 dimensions might be only a surface, only the visible skin of a deeper, layered reality begins to shimmer with possibility. You see, when we talk about dimensions, we don't just mean directions you can walk in. We mean the fundamental arenas in which the universe expresses itself. Length, width, height, and time. 4 dimensions. That's the picture we live inside. It feels complete because it feels familiar. But that familiarity may simply be a limitation of perspective, not a limitation of the universe. And string theory, that bold and delicate mathematical framework, suggests that the universe might contain far more dimensions, 10, perhaps 11, not just extra directions, but entire geometric realms curled tightly into spaces so small they remain hidden from view. It's not just that we can't see them, it's that every atom, every particle, every pulse of energy is blind to them unless it vibrates in just the right way. Well, imagine, if you will, that you're holding a sheet of paper to an ant. That sheet has 2 dimensions. The ant can walk forward and sideways, but not up. The 3rd dimension exists, but the ant doesn't use it. And now imagine that the sheet of paper is actually a rolled up tube. The ant might walk in circles without ever realizing it's looping through an extra dimension. The path seems straight but is not. The space seems simple but is not. That is the idea of compactified dimensions. Hidden, folded, curled. So in the fabric of space-time, there may be tiny curled structures, vastly smaller than atoms, shaping the behavior of particles and forces without ever revealing themselves openly. And the most astonishing part is that the properties of particles, their mass, their charge, their spin, may emerge from the geometry of these tiny dimensions. The universe we see, the physics we measure, might be the shadow of a deeper, multidimensional object. It's not just a poetic metaphor, it's one of the most serious proposals in theoretical physics. And in this view, gravity behaves differently from the other forces, not because it is weak, but because it spills into these extra dimensions, like water escaping through tiny cracks in a floorboard. Gravity might feel diluted in our world because it disperses across multiple directions we cannot access. Um, and that might also explain why gravity is so much weaker than electromagnetism. A magnet can lift a paperclip against the entire gravitational pull of the Earth. That, that imbalance remains one of the great mysteries of physics. But if gravity leaks into dimensions beyond our own, then what feels weak here might be strong elsewhere. And, well, this idea opens a profound possibility. If we could probe energies high enough, far beyond what our current accelerators can reach, we might momentarily excite modes of vibration that depend on these extra dimensions. We might see particles behaving strangely, unexpectedly. We might detect missing energy, vanishing into directions our detectors cannot follow. Whether it, whether it exists at all is still unknown, but the search continues. So, so how do scientists even begin to test for hidden dimensions? One method is to look for deviations in gravity at very small scales. If gravity changes its behavior when distances shrink below a certain threshold, that could hint at extra dimensions influencing the force. Experiments have tested gravity down to tiny fractions of a millimeter, and so far, everything behaves as expected. But the window remains open. The next generation of precision measurements might reveal subtle shifts, tiny whispers from hidden realms. And there is another approach, colliders, vast machines that smash particles together at tremendous energies. In principle, if extra dimensions exist, some of the energy from these collisions might disappear into them. Not destroyed physics forbids that, but transferred into motion along dimensions we cannot perceive. Imagine throwing a ball and watching it vanish midair, not because it ceased to exist, but because it rolled into a hallway you didn't know was there. That is what physicists look for, missing energy that signals hidden directions. And then there are the theoretical hints. The mathematics of string theory does not simply allow extra dimensions, it requires them. The equations fall apart without them. It's not a matter of preference, but of internal consistency. The symphony of the universe, as described by strings, needs enough room to vibrate. 4 dimensions are too few. 10 or 11 allow the melodies to harmonize. Well, these extra dimensions might also solve some deep puzzles, like the hierarchy problem, the vast gulf between the strength of gravity and the other forces, or the question of why fundamental particles have the masses they do, or why the universe has the structure it displays today. That richness of explanatory power keeps extra dimensions alive as a serious idea, even if the evidence remains elusive. But there is an even stranger possibility. Perhaps the dimensions are not simply curled, but dynamic. Perhaps they expand and contract. Perhaps they influence cosmic evolution. In some models, the birth of the universe itself, the Big Bang, might have been triggered by the collision of higher dimensional membranes. Our universe could be one sheet in a vast stack, each sheet a cosmos with its own dimensions and laws. And if that is true, then our reality is not just three-dimensional, but part of a higher dimensional architecture. We might be floating in a larger space, unaware of neighboring universes, just micrometers away along invisible dimensions. Not just other worlds, but other entire realities brushing past ours. And it's dizzying to imagine. A cosmos layered like pages in a book. A universe where proximity does not depend solely on the 3 directions we know, but on hidden coordinates that lie beyond our senses. And, even the forces that shape matter might twist through these extra dimensions. Electromagnetism might remain confined to our 3-dimensional slice, while gravity roams freely. Strings vibrating in different patterns might stretch around these compact spaces, producing particles with exotic properties. So, so what does this mean for us, for our understanding of existence? It means that what we see might be only a fraction, a thin cross-section of something much grander. The universe might not be limited by our intuition. It might be a multi-dimensional landscape where the familiar laws are but local guidelines. And when you think about it, there's something profoundly humbling about this possibility. It's not just that the cosmos is larger than we know, it's that reality itself may have architecture beyond our imagination. We grow older, clocks tick, but dimensions do not reveal themselves simply because we ask. They require careful probing, deep mathematics, and an openness to possibilities that challenge the boundaries of our everyday experience. And in 2025 and beyond, new experiments may test these ideas with renewed precision. Whether they find hints of hidden dimensions or not, the act of searching pushes our understanding forward. But here is where the thought becomes philosophical. If the universe has hidden dimensions, then our perception, our lived sense of space, captures only a thin slice of truth. It's not just out there, it's in here, in the way our minds evolved to navigate a world that only reveals part of itself. And the deeper we follow this thread, the more we begin to sense that the nature of space, of forces, of matter might be rooted in something even more fundamental than dimensions. What if space itself, whether three-dimensional or 10, emerges from something deeper? What if the geometry we measure, the dimensions we infer, the forces we feel, all arise from patterns of information? What if the universe is not built from space, but from relationships, entanglements woven into a network that gives rise to geometry as a secondary effect? And that question, that quiet, profound shift in thinking, leads us gently toward the next chapter, toward the idea that space-time itself might not be the foundation of reality. So let's move forward and let's explore what happens when we imagine the universe not as a place, but as information, humming beneath everything we see. Well, as we drift forward from the question of hidden dimensions, there's a feeling strange, persistent, that the universe is quietly holding something back. Something vast, something everywhere, something that shapes the cosmos on the grandest scales while remaining almost impossibly elusive. And when we finally name it, the words feel small compared to the mystery, dark matter and dark energy. 95% of the universe, and we don't know what it is. You see, the more we map the cosmos, the more we realize that what we see, the stars, the gas, the glowing webs of galaxies, accounts for just a thin sliver of reality. That realization arrives like a quiet astonishment. It's not just that something is missing, it's that almost everything is missing. We are living in a universe built mostly from shadows we cannot touch. And the story begins with a simple observation. Galaxies spin too fast. Their stars should be flung away into space, as if the cosmic carousel were turning with reckless speed. And yet the galaxies hold together, bound by a gravitational glue stronger than what their visible mass can provide. Something unseen, some additional mass, must be holding them intact. Well, that invisible mass is what we call dark matter. Not because it's dark the way night is dark, but because it does not interact with light at all. Whether it exists as particles or something more exotic is still unknown, but its gravity is undeniable. And, the evidence didn't stop with spinning galaxies. Clusters of galaxies, the largest gravitationally bound structures in the universe, behave as though they contain far more mass than the stars and gas we observe. Even more striking are the gravitational lensing images, where distant light bends around clusters in patterns that reveal hidden mass like a fingerprint. The bending is far too strong to be caused by visible matter alone. Something else must be shaping the curvature of space. So, dark matter reveals itself not through light but through gravity. It is the silent sculptor of the cosmic web. Without it, galaxies would never have formed, stars would never have gathered, planets would never have emerged. The universe would be an airy fog of hydrogen, too diffuse for structure. And as strange as it sounds, dark matter might pass through your body every moment without leaving a trace. It does not collide with atoms, does not scatter off electrons, does not shine, does not glow. It simply drifts through space, obeying only gravity. And that raises questions that feel almost existential. What is matter if most of it does not behave like the matter we know? What is reality if 95% of its contents remain undetected except through indirect clues? Physicists have built detectors deep underground, shielded from cosmic rays, searching for the faintest hints of dark matter, particles colliding with normal matter. But the detectors remain silent. Years pass, we grow older, clocks tick, and still no confirmed detection. But the silence itself is informative. It pushes theorists to explore more exotic possibilities, particles that interact only weakly or not at all, hidden sector forces, layered dimensions where dark matter moves more freely than ordinary matter. Perhaps the dark sector is not empty, but rich with its own interactions, its own structures, its own internal complexity. And, well, as mysterious as dark matter is, it is almost straightforward compared to dark energy. Dark energy is not matter at all. It is not mass. It is not something that clusters. It is something far stranger, a force or a property of space that drives the expansion of the universe to accelerate, not slow down, accelerate. So if dark matter holds things together, dark energy pushes them apart. The discovery arrived at the end of the 20th century when astronomers measured distant, exploding stars, standard candles that reveal how fast the universe was expanding in the past. To their shock, the data showed that the universe was not coasting or slowing, it was speeding up. Imagine throwing a ball into the air and watching it rise faster and faster instead of falling back down. That is the behavior of the cosmos. Expansion is not just continuing, it is accelerating. Something is pumping energy into the fabric of space, urging it outward. And the simplest explanation is the cosmological constant, a term Einstein once introduced, then abandoned to stabilize his equations, a constant energy density that pervades space itself. As space expands, more of this energy appears, driving further expansion in a kind of self-reinforcing cycle. Well, that explanation works mathematically, but it leaves a deep question. Why does this constant have the tiny value it does? If it was slightly larger, galaxies could never have formed. If it was slightly smaller, the universe might have collapsed early. The cosmological constant is like a dial set to a shockingly precise value, and we don't know why. Other theories propose dynamic fields, like quintessence fields that evolve over time. These fields could change the rate of expansion, speed it up, or slow it down. They might interact with matter, or remain forever hidden. They might reveal themselves only in subtle variations in cosmic expansion. So So dark energy might not be constant at all. It might be alive, shifting as the universe grows. And then there are radical ideas. Perhaps dark energy is the effect of extra dimensions unfolding, or the curvature of high dimensional space, or a sign of vacuum energy bubbling unpredictably from quantum fluctuations. Or, in some scenarios, the universe might be transitioning between states, like water freezing or boiling, and the current accelerating expansion is part of that cosmic phase change. Whether any of these explanations is correct is unknown, but the stakes are enormous because dark energy controls the universe's fate. If it keeps accelerating, galaxies will drift farther apart until the night sky becomes empty of everything except our own cosmic neighborhood. If it grows stronger, it could one day tear apart galaxies, stars, planets, even atoms, in a violent expansion known as the Big Rip. If it weakens, expansion could slow, perhaps even reverse. And the most haunting possibility is vacuum decay, the idea that the universe exists in a false vacuum state, a metastable energy configuration that could suddenly transition to a lower state, rewriting physics at the speed of light. Not just destruction, but transformation, reality itself redefined. Well, these scenarios sound dramatic, almost unsettling, but they come from the attempt to understand why the vacuum of space has the energy it does. The vacuum is not empty. It is restless, seething, alive with fluctuations. That restless energy might be the source of cosmic acceleration. And, well, here is a thought that often lingers with me. If dark energy shapes the expansion of space, and if dark matter shapes the formation of galaxies, then the visible universe, the part we know, is a thin compromise between two vast, invisible influences. It's not just that we see little, it's that what we see depends entirely on what we cannot see. Take the cosmic web, that immense network of filaments and clusters. Dark matter forms its scaffolding. Normal matter falls into the gravitational wells created by that invisible structure. Galaxies form where dark matter is densest. The universe's shape, its architecture, is determined by an invisible grid. And on the largest scales, dark energy stretches the web apart, thinning the filaments, widening the voids, accelerating the cosmic drift. So the universe is shaped by a tension, dark matter pulling structure together, dark energy pulling space apart. A cosmic tug of war that defines everything we observe. And in 2025 and beyond, telescopes and space missions continue to measure the effects of dark energy with greater precision, mapping expansion across cosmic history. Perhaps those measurements will reveal clues, subtle shifts hinting at new physics, and underground detectors grow more sensitive, searching for dark matter particles. Perhaps one day a particle will collide with an atom, leaving a faint signal, a whisper from the dark side of the universe. Whether it exists as particles, fields, or geometric features of space, the search continues. But as we stand here, contemplating these invisible forces, another question emerges, a question deeper than matter or energy. If 95% of the universe is unseen, then what is space itself made from? What gives rise to the geometry of space-time? What shapes the very grid on which matter and energy exist? And if information, entanglement, and quantum relationships lie beneath space, then perhaps the universe is not built on emptiness, but on something richer. So let's move gently forward into the next chapter toward the idea that space may not be fundamental at all, that geometry itself may arise from patterns woven beneath the surface of reality. Well, when we step from the realm of dark matter and dark energy into this next, quieter frontier, there's a subtle shift, almost like the air changes around us, and it becomes harder to say where physics ends and philosophy begins. Because now we're asking something unusually intimate about the universe. What if space itself is not fundamental? What if the vast emptiness between galaxies, the fabric that stretches and bends and carries light across billions of years, is not actually the foundation of reality at all? You see, for most of human history, space was simply there, a stage, a backdrop, a container that held stars and planets the way an ocean holds currents. But that view has slowly dissolved as we've looked deeper. First, Einstein taught us that space is not passive, but dynamic, shaped, and stretched by mass and energy. And now, in the 21st century, a new idea is rising, quietly, cautiously, suggesting that even Einstein's space-time might not be the final layer. And the idea comes from a surprising place: quantum information, entanglement. The strange, almost mystical link between particles that allows them to share states instantly, no matter how far apart they drift. And here's where it gets astonishing. Some physicists are beginning to suspect that space, its geometry, its curvature, even the distance between points, might emerge from patterns of entanglement, that the universe is woven not from stuff, but from relationships, not from points, but from connections. Well, imagine that instead of a grid of coordinates, the universe is a vast network of quantum events, each linked by threads of information. If you increase the entanglement between two regions, the distance between them shrinks. If you decrease the entanglement, the distance grows. Space stretches or tightens like fabric, not because of geometry itself, but because of the strength of quantum correlations. It's not just a poetic metaphor. It's a serious proposal. Space-time equals entanglement. So if you were to look beneath the smooth continuum of space, you might see something granular, something woven, something like a tapestry of quantum bits flickering in and out of alignment. The geometry we experience is the shape formed by those threads. And this leads to a striking claim: empty space is never truly empty. Even the vacuum, what we think of as nothing, is alive with entanglement, a restless sea of quantum relationships humming just beneath the threshold of observation. And if space emerges from entanglement, then gravity might emerge from it too. Some researchers propose that when entanglement patterns warp, we perceive that warping as curvature, gravity. It's not that mass bends space, it's that mass disrupts information flow, and that disruption appears to us as curved space-time. It's not just that geometry equals entanglement, it's that gravity itself might be an entropic force, a statistical tendency arising from the universe's drive toward equilibrium. Well, if this is true, then we must rethink everything. We must rethink what a distance truly is. We must rethink what it means for two events to be separated. We must rethink the very notion of locality. That conviction grows even stronger when we consider the holographic principle, the idea that information inside a region of space is encoded on its boundary. If that's the case, then the world we perceive in 3 dimensions might be the emergent result of information stored in 2 dimensions. So the universe we touch might be the shadow of a deeper informational structure, not just matter emerging from fields, but space emerging from quantum bits. It's not out there, it's in here, in the relationships, in the patterns. Um, think of it like this. If you observe a group of tangled strings, the shape of their knots defines a surface. In the same way, the entangled quantum states define a geometry. The universe becomes a kind of loom, weaving space from invisible, interlaced threads. And well, this idea also helps explain something puzzling about black holes. When matter falls into a black hole, the interior collapses, but the information describing that matter seems to be stored on the event horizon, not inside, but on the boundary, a literal hologram. If information defines geometry, then the boundary of a black hole is not merely a surface, it's the repository of everything that once fell inside. In this light, the black hole is not a region of crushed space, but a dense archive of entanglement patterns. We grow older, clocks tick, but black holes preserve information in their surface structure. This is why many physicists believe the interior of a black hole is not fundamental, it's emergent, a kind of projection created by entanglement. The core mystery becomes not what happens inside, but how the information arranges itself on the surface. And the same logic might apply to the entire universe. If the cosmos has a distant boundary, a cosmological horizon, then perhaps all the information that defines our reality is encoded there, written into the far edge of what we can observe. And inside that boundary, the geometry unfolds from those encoded patterns, creating the space we inhabit. In that sense, the universe is not a place, but a story, being told by information. Well, even the structure of the cosmic web supports this radical view. The distribution of galaxies, the formation of clusters, the stretching of voids all may emerge from deep informational rules, not from pre-existing space. Space is the stage that arises when the script of entanglement becomes dense enough. It suggests that space is not a container, but a consequence. And once you begin to see space as emergent, another strange question arises. Could time be emergent too? If distances are the result of entanglement patterns, could the arrow of time be the result of information spreading, copying, becoming less ordered? That's the thing. Entropy, the measure of disorder, might not just govern thermodynamics, it might govern time itself. The direction of time could be tied to the growth of entanglement, the deepening of informational structure. As the universe expands, entanglement grows and time flows. So, the past may be the region of lower entanglement, and the future, the region where entanglement has grown. Time unfolds like a tapestry weaving itself. And although these ideas seem abstract, they hint at something deeply human. If the universe is built from relationships, then perhaps consciousness, our own awareness, emerges from similar patterns. Perhaps the universe and the mind are reflections of the same informational principles, echoing each other across scales we have only begun to understand. And yet, as radical as this view is, it prepares us for something even stranger. Because if space-time is emergent, if geometry arises from information, then the holographic principle is not an exception, it might be the rule. Well, once you accept that, it becomes almost inevitable to ask the next question. If our three-dimensional world is a projection of information encoded on a surface, could the entire universe be a hologram? And that question, shimmering at the edge of mind and physics alike, is the doorway to the next chapter, where we step fully into the idea that our universe might not be what it seems, that its depth might be an illusion, and that reality itself might be written on a distant cosmic screen. Well, when we arrive at this threshold, this shimmering idea that space-time itself might be woven from information another, even stranger doorway opens, and uh, stepping through it feels a little like realizing that the room you've lived in all your life might actually be a projection on a screen. Because now we're asking something almost unsettling in its boldness. If geometry emerges from entanglement, then could our entire three-dimensional universe be a kind of hologram? You see, the holographic principle isn't a metaphor. That's the part that catches you off guard. It's a precise mathematical insight born from the most extreme objects in the universe, black holes. And the story starts with a paradox. Well, black holes swallow matter, swallow light, swallow information. For decades, physicists believed that whatever fell in was gone forever. But a puzzle emerged. If matter falls into a black hole, what happens to the information that described it? Quantum theory insists that information cannot be destroyed. Gravity seemed to suggest it could. Two great pillars of physics, contradicting one another. And in the 1970s, Jacob Bekenstein proposed something astonishing. The entropy of a black hole, the measure of how much information it can hold, is proportional not to its volume, but to the area of its surface. That's strange. That's deeply strange. It suggests that everything about what lies inside a black hole could be encoded on its boundary. Stephen Hawking then added another piece to the puzzle by showing that black holes radiate. They emit energy. They evaporate. And, well, that intensifies the paradox. If the black hole disappears, where does the information go? This is where the holographic idea takes its first breath. So if all the information describing the interior is encoded on the event horizon, then the three-dimensional interior is not fundamental, a kind of emergent projection. The boundary holds the truth. The volume is the illusion. The black hole is a hologram. And here is where the universe surprises us again, because this principle doesn't just apply to black holes. It applies to space-time regions in general, to the entire universe. What if everything we perceive, the space around us, the distances between stars, the structures stretching across billions of light years, are all emergent from information encoded on a distant cosmic boundary? Well, it sounds impossible at first, but the mathematics of string theory uncovered something profound in the 1990s, a duality between a gravitational universe in 3 dimensions and a non-gravitational quantum system in 2 dimensions. 2 descriptions, one reality, a world with gravity mapped perfectly onto a lower dimensional world without it. It's not that one is truer than the other, it's that the universe allows 2 perspectives, one with volume, one without, and both describe the same physics. And that is the essence of the holographic universe. It's not just that the universe can be described as a hologram, it might be one. So imagine that the cosmos we inhabit is the projection of quantum information inscribed on a cosmic horizon. That horizon is so far away, so spread out over billions of light years that we never see it, just as a fish inside a bowl doesn't notice the glass. But its presence defines everything inside. Think of the cosmic microwave background, the most ancient light we know. It fills the sky like a boundary, the farthest we can see. Some physicists wonder whether information is encoded there, woven into the statistical patterns of its fluctuations. If the universe is holographic, that ancient glow might hold the imprint of the 2-dimensional surface from which our 3-dimensional experience emerges. And even now, experiments on Earth are trying to detect signs of this holographic nature. Some physicists look for a gentle jitter, a holographic noise in precise laser interferometers. If space-time is not fundamental but pixelated at the smallest scales, then this jitter might reveal the resolution of reality, the grain of the cosmic screen. Well, nothing definitive has been found yet, but the very attempt shows how seriously the idea is taken. Whether holographic noise exists, well, whether it exists at all, remains uncertain, but the search continues. That's the thing with the holographic universe. It forces us to rethink what it means to be inside something. If the universe is encoded on its boundary, then interior and exterior are illusions produced by perspective. The inside of the universe might not truly be inside anything at all, but a manifestation of deeper rules on the horizon. Um, and this raises another thought, one that's harder to shake. If our universe is a hologram, then distance itself becomes secondary. The vastness we experience might arise from layers of encoded information unfolding into our three-dimensional perception. The idea that galaxies are billions of light years apart might be the emergent result of how that information maps into space. And it suggests something beautifully humbling. The universe is not just large, it is deeply structured, deeply encoded. Space is not emptiness, it is meaning expressed geometrically. Well, um, well, the holographic principle also gives new insight into why black holes, despite their simplicity, seem to encode vast amounts of information. Their event horizons become archives, and their evaporation through Hawking radiation becomes a process by which that information escapes, transformed but not destroyed. The universe protects its information even in the most extreme environments. So, so if black holes obey the holographic principle, and if the cosmos itself follows similar rules, then perhaps everything, stars, planets, life, exists as part of a grand informational tapestry. And the philosophy hidden in this physics is strangely gentle. If we are made of information, then we are also made of relationships, quantum ties stretching across the fabric of reality. Our existence is not just matter arranged in space, but the result of deep underlying patterns. And as we drift deeper into this idea, another frontier starts to shimmer just ahead, the nature of black holes themselves. Because holography doesn't just describe the universe. It reshapes everything we thought we knew about black holes. It tells us that their interiors may be illusions, that their cores might contain no singularity at all, that the event horizon stores everything that ever fell in, that black holes might bounce, collapse, transform, or even connect to distant regions of space. It leads us to the threshold of the most extreme, most unforgiving, most paradox-rich entities in the universe. So let's move gently toward that abyss, toward the place where space-time breaks down, where gravity becomes infinite, where information fights for survival. Let's step softly into the next chapter, into the dark heart of the cosmos, where black holes rewrite the rules of reality. Well, when we step from the holographic horizon toward the dark heart of the cosmos itself, there's a moment quiet, almost breathless, where the universe seems to pause with us. And in that pause, you can feel it, that sense that we're approaching something different now, something heavier, something that doesn't just bend the rules of physics, but, well, tears them, stretches them, folds them into shapes we barely have language for. Because now we're entering the realm of black holes, those places where space-time collapses into mystery. You see, a black hole is not just an object. It's not just a dead star or a gravitational trap. A black hole is a question posed by the universe to anyone brave enough to look closely. That's why this chapter feels different from the others. Everything we've discussed so far, horizons, dimensions, holograms, comes together here, where the laws of nature unwind. And the strange thing is, black holes begin in the most ordinary way. A massive star, burning nuclear fuel in its core, gradually exhausts that fuel. Gravity wins, the star collapses inward, and, and then something extraordinary happens. If the collapsing core becomes dense enough, its gravity grows so strong that not even light can escape. The boundary of this region is what we call the event horizon. Well, what lies inside that horizon? That's the haunting part. According to classical physics, the matter collapses into a singularity, a point with no size and infinite density, where the known laws of physics break down. But that idea, um, when you feel it closely, feels more like a confession than a description. It's the universe saying, I don't know what happens here. So inside a black hole, space-time curves to its limits. Distances lose meaning. Time twists. Directions fold. It's not just that nature behaves differently, it's that nature, as we know it, disappears. And, well, that's only the beginning of the strangeness. Because from the outside, black holes look deceptively simple. Entire stars crushed down to objects defined by only three things: mass, spin, and charge. No surface, no texture, no features, just smooth, perfect darkness. They erase the details of everything that fell in, or at least that's what we used to think. Then came the great paradox. Does information disappear in a black hole? We know from quantum theory that information cannot be destroyed, but black holes seem to swallow information and then evaporate through Hawking radiation, radiation that appears random, carrying no obvious hint of what fell inside. It creates a contradiction that sits right at the center of physics. Gravity insists on one outcome, quantum mechanics insists on another. And the universe, somewhere beneath our theories, knows the truth. And this paradox launched decades of debate. One proposal after another tried to save the rules of physics. Some suggested information hides behind the horizon until the last moment. Others suggested subtle correlations in Hawking radiation carry it out. Some even imagined firewalls, blazing barriers at the event horizon that destroy anything falling in, preserving information at the cost of breaking Einstein's smooth space-time. None of these solutions is painless. Each bends something we thought was fundamental. But holography, the idea we explored earlier, offered a softer resolution. If the interior of a black hole is not fundamental, if it emerges from information encoded on the horizon, then nothing is lost. The black hole becomes a storage device, a library, a cosmic ledger keeping track of its past. When it evaporates, the information leaks back out, scrambled but not destroyed. Well, that idea doesn't just solve the paradox, it transforms our entire understanding of black holes. So what is a black hole? Is it a region of crushed matter? Is it a holographic screen storing information? Is it a doorway to another part of the universe? Or perhaps all of these at once? Let's step even closer. The event horizon is not a physical surface. You cannot touch it. There's nothing there. And yet, it behaves as though it's the most important membrane in the cosmos, a surface of no substance that holds the memory of everything inside, a shimmering boundary between what we can know and what we cannot. And, well, deeper in classical theory predicts a singularity, but many modern ideas challenge that. Some suggest that instead of a singularity, there might be a quantum core, tiny but finite, where space-time's graininess prevents infinite collapse. Others propose that black holes might bounce, reversing collapse and turning into white holes, objects that expel matter instead of swallowing it. It's not just theoretical whimsy. These models arise from attempts to merge gravity and quantum physics. Imagine a collapsing star reaching enormous density, enough that quantum gravitational effects kick in. Instead of continuing to collapse, it rebounds, releasing energy outward, not in our universe, but in another region of the larger space-time. A black hole becomes a tunnel, a bridge, a passage from one geometry to another. And in some early universe models, tiny primordial black holes may have formed just after the Big Bang, seeded by quantum fluctuations. Some might still drift through the cosmos today, cold, ancient, invisible. Others might have evaporated, leaving behind subtle signatures in the cosmic background. Well, what role did these primordial black holes play? Could they be part of dark matter? Could they have shaped the earliest galaxies? Could their evaporation have left traces that we might detect even now? It's remarkable to think that ancient black holes, smaller than mountains, might still be whispering across the universe. But black holes are not only relics, they are architects. The supermassive black holes at the centers of galaxies, millions or billions of times the mass of the Sun, shape the fate of cosmic structures. Their jets and winds carve the gas around them, regulating star formation. Their gravity anchors the galaxies that spin around them. And the Milky Way has one too, Sagittarius A star, quiet now but once likely far more active. We orbit it. Our night sky exists in its gravitational domain. Our galaxy would be unrecognizable without it. So the universe we know, the stars we see, the arm of the Milky Way that cradles our world, all exist because of a black hole in the center. Black holes don't just destroy, they create structure. They shape worlds. They seed galaxies. They govern the architecture of the cosmos. That duality is part of what makes them so compelling. They are not monsters. They are engines. They are the dark hearts beating at the center of cosmic evolution. And yet, for all their influence, they remain the ultimate symbols of ignorance. The place where our equations break. The place where we must invent new physics. The place where the universe challenges us most directly. Well, when you stand at the edge of a black hole conceptually, at least you're standing at the edge of knowledge itself. And it makes you wonder, if black holes encode information on their surfaces, could the universe itself operate similarly? Could cosmic evolution be shaped by informational rules at the boundary of space-time? Could every horizon, cosmic, black hole, quantum, hint at something deeper? That's the thing. Black holes are not just astrophysical objects. They are clues. They are signposts. They point toward something larger, something beneath space-time, something we have not yet fully grasped. And once you follow that thought, another idea begins to emerge. If black holes challenge our understanding of space-time, then what happens when we consider the universe beyond them, beyond our own cosmic bubble? Do other universes contain black holes with different properties? Do their horizons encode different informational rules? Do they follow laws unlike ours? So from the singular darkness of black holes rises an even grander question. If our universe is one bubble in a vast multiverse, then what lies beyond the boundary of our cosmic domain? And that question, spacious, unsettling, filled with wonder, guides us gently toward the next chapter, where we step beyond our universe and into the possibility that it is only one bubble among many. Well, when we drift from the dark heart of me, black holes, into the possibility that our universe might be just one bubble among countless others, there's a kind of hush, like the cosmos is holding its breath. And in that hush, something vast begins to unfold. Because now we're not just asking what lies inside our universe, we're asking what lies beyond it. That is the question at the core of the multiverse. You see, when cosmologists first studied inflation, the rapid expansion that occurred, fractions of a fraction of a second after the Big Bang, they noticed something strange. Inflation doesn't really want to stop. Um, Once it starts, the mathematics suggests it keeps going in most places forever. So, so even though inflation ended in our region and allowed galaxies and stars and planets and life to form, in other regions it may still be roaring on, stretching space faster than light, creating new pockets of reality, and each of those pockets could cool and form their own universes. Not just distant places, but distinct worlds with their own laws, their own constants, their own possibilities. The multiverse becomes not just theory, but an inevitable consequence of eternal inflation. Well, imagine a vast cosmic ocean, endlessly churning. In that ocean, bubbles form, each bubble expanding, each bubble becoming a universe. Our universe is one bubble, another over there, another beyond that, and well, the ocean goes on forever, inflating, birthing new universes, endlessly. It's not just many universes, it's an ever-growing foam of universes. So, so what makes these universes different? That's where the landscape of physics comes back into play. In some bubbles, the constants might be slightly different. Gravity could be stronger or weaker. The cosmological constant could be enormous, tearing the universe apart before stars form, or negative, causing rapid collapse. In some universes, atoms might not be stable. In some, chemistry might never arise. In others, exotic particles might dominate. And that raises a quiet but profound idea. We exist in this universe because this universe allows life. It's not that the universe was designed for life, but that life emerges only where conditions permit. It's not just anthropic reasoning, it's a selection effect. Out of potentially infinite universes, we find ourselves in one of the rare bubbles where stars burn long enough, where atoms form, where entropy grows slowly, where complexity has time to blossom. And that makes our universe feel less like the center of creation and more like one hospitable island in an enormous archipelago of realities. Well, but the multiverse idea is not without criticism. Some scientists argue that if other universes can never be observed, then the theory is untestable. Others point out that inflation, though compelling, might not be the final word on cosmic origins. And some worry that if every possible universe exists, then explanation itself becomes diluted. Anything can happen somewhere. It, it, it's a fair concern because science thrives on testability, on predictions, on falsifiability. And yet, hints of the multiverse might be closer than we think. Some suggest that collisions between universes in the early cosmos could leave marks, circular scars, in the cosmic microwave background. Others propose that subtle anomalies in that ancient light, patterns we struggle to explain, might be evidence of influences from beyond our bubble, and gravitational waves, ripples in space-time, could, in theory, carry echoes of such collisions. A faint signature from another universe brushing against ours billions of years ago. Whether it exists at all is still uncertain, but the search continues. So let's imagine for a moment what different universes might be like. In one, perhaps the electromagnetic force is slightly weaker. Stars burn cooler, longer, planets form differently. Chemistry dances to a slower rhythm. In another, the strong nuclear force might be so strong that hydrogen fuses too easily, causing stars to be brief. Brilliant explosions, no time for life to arise. In yet another, dark energy could be so intense that galaxies never form. Space rips apart too quickly. No light, no stars. just endless expansion. And somewhere in this cosmic mosaic, our universe sits a fragile balance of forces, not too strong, not too weak, not too curved, not too flat, not too chaotic, not too empty, just stable enough for stars to ignite and persist, just calm enough for planets to coalesce, just generous enough for life to breathe, wonder, ask questions. And the stunning thing is that inflation might produce every possible variation, every possible arrangement of physics, somewhere out there in the ever-expanding sea. Well, that leads to a deeper, more philosophical question. If infinite universes exist, does that mean infinite versions of us exist? Infinite Earths? Infinite histories? Or does each universe differ so drastically that the branches only resemble ours from afar? That uncertainty reveals something about our desire to place ourselves at the center of things. The multiverse challenges that deeply. It tells us that our universe is not unique, that our story is one among countless stories. It's not out there, it's in here, in the way we cling to meaning, to significance. And if the multiverse is real, then the boundaries of science shift. We are no longer studying the universe, we are studying a universe, a single bubble in an endless field of possibilities. And, well, from this perspective, fine-tuning becomes less mysterious. If enough universes exist, then the improbable becomes inevitable. Rare conditions become ordinary when the sample size is infinite. But then another thought arises, delicate, unsettling. If the multiverse truly exists, then can universes interact? Can information pass between them? Can one bubble influence another? Or are they forever isolated, drifting in the ocean of inflation? So far, the mathematics suggests that universes are causally disconnected. Light cannot cross between them. Gravity cannot leak across the boundaries. Each bubble is sealed off by inflation. But some proposals hint at bridges, at wormholes that might form between universes. At quantum, tunneling events where one universe births another. At cosmic transitions where vacuum states shift and spawn new bubbles. And if universes can be born from other universes, then perhaps ours is not the first. Perhaps it is part of a lineage, a cosmic family tree, stretching back through eons of inflationary epochs. Well, consider this. If inflation is eternal to the future, it might be eternal to the past as well. Our universe could be one generation in an endless chain of cosmic births. The Big Bang becomes not the absolute beginning but a local event, a spark in a much larger fire. That idea humbles me. It stretches our imagination beyond anything we can test directly, yet still grounded in the mathematics of cosmic expansion. But let's pause for a moment. If our universe is one bubble in a multiverse, then what does that mean for its ultimate fate? Are universes long-lived or brief? Do they collide? Do they fade? Do they seed new universes in their final moments? And that question about endings, about futures, pulls us gently toward the next frontier. Because if the multiverse represents the grand structure of all that could exist, then our own bubble still has a story, a destiny, a fate determined by dark energy, by entropy, by the delicate balance of forces that shaped our world. So let's step softly now from the infinite foam of universes to the long, slow arc of our own cosmic future. Let's drift toward the next chapter, toward the question of how the universe ends. Well, when we drift from the endless sea of multiverses back toward our own small cosmic bubble, there's a moment soft, almost trembling, where we sense that the universe might still be whispering to us. And uh, it's a whisper from the earliest dawn of time, from a moment before stars, before atoms, before light took its first breath. Because now we're asking whether the universe has left any traces, any scars, any deep imprints of what happened before the Big Bang. That, that question feels almost forbidden, almost too delicate to touch. Yet it lingers in every conversation about origins. You see, the cosmic microwave background, the faint afterglow filling the sky, is the oldest light we can see, a soft relic from when the universe was only a few 100,000 years old. But beneath its glow, um, there might be older patterns hiding, patterns that didn't arise from our universe alone, patterns that might be echoes, remnants, signals carried across unimaginable epochs. And well, the first hint comes from something subtle: symmetry. The cosmic background isn't perfectly uniform. It has tiny variations, ripples in temperature and density, and those ripples form a kind of cosmic fingerprint, a fossil of the early universe. But when scientists examined the patterns closely, they noticed anomalies, unexpected features, strange alignments, cold regions that seemed too cold, hot spots that seemed too coherent, and perhaps the strangest of all, large circular patterns that some researchers suspect could be scars imprints from events that occurred before the Big Bang. Well, imagine two universes brushing against each other in the multiverse sea. The collision might leave a mark, a ring etched into the primordial radiation. Some scientists believe they've found such rings. Others argue the data is inconclusive. Whether it exists at all remains uncertain. But the idea lingers, like a ghost, in the data. And that's not the only clue. There's also the dipole asymmetry, a strange imbalance in the cosmic background that shouldn't be there. One side of the sky appears slightly different from the other, as if something nudged the universe before it began to expand. Some suggest it could be a leftover signature from a pre-existing structure, a kind of gravitational pull, echoing from a time when our universe was not yet born. So what could cause such features? One possibility is that our universe from a previous cosmological phase, a bounce. Instead of beginning from nothing, perhaps the universe collapsed, compressed, and then exploded outward again. In such a model, faint remnants of the pre-bounce cosmos might survive distorted, dim, but still present in the background radiation. And those remnants could explain unusual patterns we struggle to understand. Another possibility comes from primordial gravitational waves, ripples in space-time itself. These waves could have been produced during inflation or even before inflation as the universe transitioned from one state to another. And gravitational waves are unique. They can pass through the opaque early universe, carrying information no light could ever convey. If we could detect those waves, those first vibrations of reality, they might reveal stories from before the universe became transparent. And some experiments are searching for them now. The faint swirl patterns in the polarization of the cosmic background might contain their signature. A curl, a twist, a whisper from before time flowed in its familiar direction. Well, but detecting them is difficult. The signals are small. They drown easily in noise. But the pursuit continues because the reward is immense. Imagine hearing the universe's heartbeat from before the Big Bang. And then there's a more philosophical possibility. Perhaps the anomalies we observe are not scars from before time, but clues about the nature of time itself. If time emerged gradually, if it wasn't fully formed at the moment of the Big Bang, then the earliest patterns might reflect this transition, a universe learning to run its clock. And, um, well, this idea brings us to another subtlety. The concept of a before may not make sense in the way we imagine it. If time emerged from a deeper informational structure, then what we call before might be more like a different phase of existence, not an earlier moment. The anomalies in the cosmic background could be footprints of that transition, a shift from a timeless realm to a time-bound universe. So what are these anomalies telling us? Circles, asymmetries, gravitational whispers, unexpected alignments. Each one could be noise, but each one could be a doorway. And that raises an even more tantalizing question. If the universe carries clues from before the Big Bang, then what kind of universe existed before ours? Was it a previous cosmic cycle, a parent universe, a collapsing cosmos that gave birth to ours, or a quantum state simmering with possibilities waiting to crystallize into space-time? It makes you pause, because these questions stretch the limits of what science can test. Yet the cosmic background, this quiet afterglow, remains our best window into that hidden realm. And the more we study it, the more surprises it reveals. The cold spot, the axis of evil, the hemispherical power asymmetry. Each anomaly challenges our simple picture of a smooth, random, inflationary universe. Well, one idea suggests that bubbles in the multiverse might occasionally collide, and the scars of those collisions might appear as concentric rings. Another idea suggests that before inflation, the universe might have had irregularities that inflation couldn't fully erase. Another idea proposes that quantum fluctuations before the Big Bang were imprinted on the space-time fabric and stretched across the cosmos. Each idea teeters between daring speculation and legitimate possibility. And, well, the truth is, we don't yet know which, if any, of these ideas is correct. We grow older, clocks tick, telescopes sharpen, yet the earliest moment remains hidden behind a veil of opacity. But the pursuit is deeply human. To listen for echoes from before the beginning, to search for footprints left by universes that may no longer exist. So as we sift through these ancient signals, we realize something profound. The universe is not just expanding outward, it's expanding backward into its own history, revealing layers we never expected to see. And as we peer deeper into that history, another question begins to form, quiet, inevitable, almost trembling with mystery. If the universe carries scars from before the Big Bang, then it must also carry signs of its ultimate fate. Could the patterns we see today foreshadow the universe's ending? Could the same physics that shaped the earliest moment also write the final one? And that question, with its dual sense of wonder and melancholy, draws us gently toward the final chapter, toward the long, slow destiny of our universe, toward the future where galaxies fade, stars die, and the cosmos decides whether to freeze, rip, collapse, or begin again. So let's move softly now from echoes of the distant past toward whispers of the far future, where the universe's ultimate fate awaits. Well, when we drift from the echoes of a universe that may have existed before ours, there's a kind of quiet that settles around the mind. And in that quiet, you can almost hear the universe breathing slow, steady, patient. Because now we're stepping into the far future, into the final arcs of cosmic time. into the question not just of where everything came from, but where everything is going. That 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 gentle shift from origins to endings feels like turning a page in a story written in starlight. You see, the fate of the universe is not just a scientific puzzle, it's a meditation. We grow older, clocks tick, galaxies drift farther apart, and the cosmos too moves through its own stages of life. It expands, cools, transforms. And one day, far, far beyond the age of stars, it will arrive at a destination shaped by dark energy, by entropy, by the delicate balance of forces that have shaped everything since the beginning. And so the question becomes, how does it end? Does it fade, tear, collapse, transform? Or, in a possibility both unsettling and beautiful, does it begin again? Well, let's move slowly through each possibility, as if tracing the final pages of a cosmic diary. One path, perhaps the most widely accepted, is the slow, cold ending known as heat death. The universe keeps expanding. Galaxies drift apart until they slip beyond each other's horizons. Stars burn out. White dwarfs cool into black dwarfs. Neutron stars and black holes dominate for a time, but even they evaporate eventually, releasing their energy into the void. And, entropy increases unceasingly. Everything spreads thin. The cosmos becomes dark, quiet, and still. Nothing can happen because everything that could happen has already been exhausted. So in this ending, time continues, but meaning fades, motion fades, temperature fades. It's not a death by violence, but by loneliness and eternal winter, where energy is too sparse for structure. Yet another path is far more dramatic, the Big Rip. If dark energy grows stronger over time, if it accelerates the expansion more and more, then eventually expansion becomes violent. Galaxies tear apart, stars tear apart, planets, atoms, molecules, everything is stretched until even space-time rips. It's a cosmic unraveling, a fabric undone by the very force that once allowed the universe to grow. And although the Big Rip depends on a specific behavior of dark energy, the mathematics doesn't forbid it. It remains one of the universe's darker possibilities. Well, the opposite fate is also imaginable, the Big Crunch. Instead of accelerating forever, perhaps dark energy weakens. Perhaps gravity, patient and persistent, eventually reclaims dominance. The expansion slows, stops, reverses. Galaxies drift back toward one another. Temperatures rise, structures collapse. And after trillions upon trillions of years, the universe contracts into an unimaginably dense state, hot, bright, violent, a mirror of the Big Bang. That collapse could, in some models, trigger a rebound, a cosmic bounce, a new universe born from the ashes of the old, matter crushed, then released, time flowing backward, then forward again. The Big Crunch becomes the seed of a new Big Bang, and the cycle repeats across eons. Whether this cycle is eternal, whether universes rise and fall like cosmic tides, remains unknown, but the idea carries a strange comfort, an ending that is also a beginning. And then there is a fate more subtle, more quantum, vacuum decay. It sounds abstract, but it's one of the most profound possibilities in modern physics. Our universe may not occupy the true lowest energy state of reality. It may sit in a false vacuum, a temporary metastable configuration. And if that's true, a shift could occur. A bubble of true vacuum could form somewhere and expand at the speed of light, rewriting all the laws of physics inside it. So everything we know, atoms, forces, chemistry, stability, could vanish in an instant, replaced by new rules. A new universe blooming within the old. No warning, no pain, just transformation. Um, Whether vacuum decay could happen is debated. It depends on the mass of elementary particles and on fields whose nature we still don't fully understand. But it reminds us that even the vacuum, the emptiness between particles, is not empty. It's a landscape with its own topography. And, and then there is the possibility of endless inflation. If inflation never fully ended, and if new universes continue to bud off from inflating regions, then our universe might one day spawn others as well. The far future could be filled with new bubbles forming in distant regions, new universes branching like leaves from an eternal tree. Well, in this picture, our universe doesn't end. It contributes. It becomes one voice in an infinite cosmic choir, and the story of creation goes on eternally, endlessly, beautifully. That 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 idea also reframes our sense of time. If universes continually emerge, then beginnings and endings lose their absolute meaning. Everything becomes part of a larger cycle, not just of matter and energy, but of entire realities. Um, but amidst these grand possibilities, we must also confront the far more immediate human emotion hidden in these questions: wonder, loneliness, awe. Because the far future of the universe is not just about physics, it's about us. It's about our desire to understand where we belong in the grand narrative of existence. And when you imagine the stars fading one by one, the galaxies receding, the structures dissolving, you can feel that subtle melancholy. The universe, once vibrant with starlight, slowly dimming, yet, in that melancholy is something else, a strange peace, a reminder that we are witnessing, not literally, but conceptually, the full arc of cosmic history, from the first spark to the final whisper. So, what does it mean for the universe to die? It means that existence itself evolves. It means that even the cosmos has an aging process. It means that we brief sparks in a long cosmic night are part of a story that extends far beyond our lifetimes. And here is a quiet truth buried in all these endings. The universe will not vanish. It will transform. It will cool, or collapse, or rebound, or decay, or expand forever. But something will remain: space, time, energy, information, perhaps reshaped, perhaps redistributed, but never truly lost. And, and that brings us full circle to the deepest mystery. If the universe can die or dissolve or start anew, then what does that say about our understanding of time? What does it say about the continuity of existence? What does it say about the possibility that even endings might be beginnings in disguise? Well, some models suggest that in the far future, as entropy reaches its maximum, the universe might undergo quantum fluctuations so immense that new universes arise spontaneously. Others propose that the laws of physics themselves evolve, allowing rebirths of different forms, and some suggest that the end is simply a transition, a doorway into something deeper. So the final fate of the universe might not be final at all. It might be part of a cycle, a rhythm, a heartbeat, far longer than any we can measure. And as we stand here at the edge of cosmic time, not in reality, but in imagination, we can feel that vastness looking back at us. The universe, in its enormity, reminds us of how small we are, but also of how astonishing it is that we can ask these questions at all. And it brings us to a final, gentle thought. Perhaps the greatest gift of contemplating the universe's fate is not the answers, but the humility that follows. The awareness that we are temporary observers in a story far too large to finish. So So maybe the end of the universe is not a conclusion. Maybe it is an invitation, a reminder that the cosmos is still unfolding, that somewhere beyond time, beyond understanding, beyond the limits of our physics, new chapters are waiting. And as we drift toward those possibilities, a new question emerges quietly, almost shyly, waiting for the next part of our journey. If the universe itself may be reborn, then what, truly, is the nature of time? And that question, soft yet immense, leads us gently toward whatever comes next.